Okay, uh, I think time is up. Good evening, everyone. Welcome to the Asia Graphics webinar, the 39th. Uh, this is Wenhan Luo, Associate Professor from Hong Kong University of Science and Technology. I'm in the session chair today. In today's webinar, we have two talks. The first one is AI-powered creative user interaction in digital and embodied space by Professor Hui Ye from Hong Kong Baptist University. The second talk is AI-native global neural rendering pipeline from concept to realization by Professor Yuci Huo from Zhejiang University. And in the following way, I will briefly introduce Professor Hui Ye. Dr. Hui is a tenure-track assistant professor from Hong Kong Baptist University. She was previously an RGC postdoctoral fellow in HKUST and CTU. She received a PhD degree from CTU under the supervision of Professor Hongbo Fu. Her research interest lies at the intersection of HCI computer graphics with a focus on novel interactive techniques, tools, interfaces, and systems for content creation, interaction design, creativity support, and end-user development. She explores these topics through emerging techniques such as Gen AI, AR, VR, spanning applications in game design, animation creation, IoT space design, embodied interaction, cultural heritage, digitalization, and artistic expression. Her work aims to lower the barriers for both novice and expert users to create and interact with digital content in different forms and across different devices. She has published in top HCI and graphics journals, including Kai, SIGGRAPH, TOG, TVCG, and IEEE ISMAR. And she has received several honors and community service recognitions, including the organization co-chair for CVM 2025, organizer for the first HKUST AI Film Festival, and the web chair for CGI 2025. Now, I will give time to Professor Hui Ye, so I will stop sharing here. Okay.
Okay. Okay. So
We cannot hear you, Professor.
now,
No, no, no.
can you hear me now?
Yeah.
Okay.
It's okay now.
Yeah.
Thanks.
Thank you. Yeah. So now it works, right? Okay. Maybe I will share again. Okay. Okay. Thank you, Professor Luo, for your invitation and the kind introduction, and thank the AsiaGraphics organization committee and organizers for the organization. And it's my great pleasure to have this opportunity to share my works and discuss with you and also learn from you all. So today, my talk is about AI-powered creative user interaction in digital and embodied space. And my research lies in the intersection between human-computer interaction and computer graphics. So let's get started with an example. That is, if we currently want to create an interactive thing like the game, here it is a very general platform game. We can input with the text for the AI coding agent, like to input a brief description of it, and it can help us to generate this kind of games that we can play with it. But if I currently want to create a more complex and a more creative game that is in my mind, it is not a very general game. So here we can say it includes some characters and it has some character animations. And I wanted the whole style of the game, wanted to refer to some existing games. And at the same time, the game mechanism is not just I press the space button, the character will be jump up. It will have some sliding animations, and it will have some special game mechanism. So sometimes I also wanted to be customized. The character I wanted to be customized. So I need to learn how to draw this kind of character. And besides all of this, if the thing becomes complex enough, I still need to use some like the agent skills. I need to learn how to incorporate or integrate this kind of skills to steer the agent to generate this kind of complex interactive things. So here is that the AI, the agent can help us to lower the barriers for the content creation and the interaction design. So here we say that from the first example, the ordinary people can create the content and interactions with the simple interaction with the simple text. But if we want to create higher quality, only intent and personalized creative interactions, that is shown in our second example, it is still needs some skills, as I described that we need to know how to demonstrate the ideas in our mind and how to add some context and how to use an agent, steer the agent. So this kind of skills is also limited to a small group of people. So targeting for this problem, someone may ask that the AI models, the AI can get smarter, it will be more intelligent. So will this gap just close itself? My answer to this question is no, because I think that with the AI getting smarter, some part of the effort can be reduced, like the trial and errors that we do not need to write the long prompt to guide the AI or what we need to do, and the AI can help us to find some tools they can use by themselves. This kind of effort can be reduced. But for another part, that is what is in our mind, what is in the user's mind is their intention. So if the AI gets smarter, but if the user cannot convey themselves, cannot express themselves, the AI still cannot understand the user's intention. So here is the intention. So here I think the bottleneck is the user interaction, is the channel between the user and the technology. So the interaction part, this part communicate between the user and technology, it will help the users to convey themselves, express their ideas to help the technology, help the AI to understand. So here the interaction is what I work on. So my vision is that in the future, everyone can create the high quality, personalized, creative content and interactions, like I show in the second example, using the intuitive and easy interaction without any requirements to the special or hard to learn skills. So I hope that everyone can create what they can create in the first example now. So within this broader goal, my current works focus on lowering the barriers to use the emerging technology like AI and AR augmented reality for the content and creation and interaction design. And to achieve these goals, I first used the human-centered approaches. Like I conducted the interviews, the content analysis, to help find what is the problem, what is the challenge for the content creation and the interaction design. And then based on the distilled challenges, I propose the novel interactive techniques, systems, and tools to help them solve the problems distilled from the first stage. And my works consists of the two complementary pillars. The first, as reflected in my talk title. So first is the AI creative interaction in the digital 2D space. And the second is the augmented reality interaction in the embodied 3D space. So here I will briefly introduce some of them. So first, in the first pillar, the first work is the MoGraph GPT. It is a work focusing on to creating the interactive things using the modular LLM and the graphical and precise control. So here we say in this figure that if we want to create this kind of game, we can say that this platform game consists of a lot of assets. We say the characters, the enemies, and the coins, and the platform, and the palm tree, and the background, and also the score. So they have a lot of assets here. And the interaction between the different assets is not that easy. It's not that simple. They have the different kind of interactive behavior between and among different assets. So if we create this kind of game, we currently can use the LM or the agent to help us translate the text into the code. But here are some problems. So to better understand what is the challenges by using the LLM to create the interactive things, we first collect the video tutorials from the online platform, and then we do the coding for it, and then we do the content analysis and find several challenges. So here is an overview of it, the problems of it. And first is the code quality. We know that the AI can generate some codes that including some errors, but with the development of the agent, currently it can help to address it by itself. Because this work is in work in the last year, so here this problem has already been solved. And second is that we say that in the same, it contains a lot of elements here. So sometimes when we want to edit some of it, we need to tell the AI what will be refined. But sometimes the code they generated will be consists as a whole, so it lacks the editing in independency. If we want to revise something, some other part will also be refined, and it is also difficult for the user to specify which one to be revised. And the third problem is the lack of graphical control. It means that sometimes we want the platform, like for example, for this platform to move just between two vertical points. So how can we specify this kind of point? We if the user does not know coding well, so she or he can just prompt to refine the prompt to make it to specify whether there is to estimate what is the position of it and to specify this kind of spatial information. And sometimes we want that, for example, this kind of land, we want it to just specify a specific in a specific region. So this kind of graphical information is difficult to be specified using the text only as input. And the last one is the lack of precise control. So if the platform moves between up and word, if we want to refine the speed of it, if we do not know programming, we still need to try it for a lot of times. So it cannot be directly precisely controlled to a specific speed. So to address these challenges, we proposed the MoGraph GPT. So uh, it it consists of a modular framework. It means that we separate the generation and the refinement for different assets. Each asset will have the LLM session, and we have a central LLM session to manage and coordinate the different interaction between the different assets. And then we allow users to specify the graphical information from the canvas directly. So here, if we want the platform to move between P1 and P2, we directly click it in the canvas. And then this kind of graphical information will be integrated into the text input. After the generation, we also provide the automatically generated sliders. Here, we have different sliders for the different parameters of the assets, and then the users can drag the sliders left and right to adjust the different the precise parameters. So here is the detailed framework of it. And we design and develop a user interface for the users. So here in the left text pane, the users can input their descriptions here. And then here in the canvas area, they can drag different assets here, specify the graphical information, including the points, line, curve, and region area. And then here, this result area shows the result, and here platform panel shows the automatically generated sliders. So here I will use an example demo video to show it.
We first upload the image elements to the scene and drag to move them to the target positions. Then input the text for Mario. We can drag the automatically generated sliders or input values for changing moving speed. We draw points P1 and P2 to specify the platform moving threshold and mention them in the text. We input the text of the interactions in the central module by clicking multiple buttons. We draw a region R1 to let cloud shake within it. And we can adjust its shaking speed using slider value input. We can further revise the cloud movement to move along a joint curve, and it updates.
So here is the demo video. We show that how we integrate the different graphical information and the precise control and the modular LLM to help novice creators without any coding background to create different kind of games. So here is the results from the user study, including the interactive demonstrations, animations, and the games. So besides the games, we also work on the creative arts. So due to the time limitation, I will not go through this work. And so next, move on to the second pillar, AR interaction in the embodied space. So here, I will also briefly introduce one work, the AR animator. So this work is about using the mobile device as a controller to create the augmented reality character animations closely interacting with the physical world. So here we can say that this is the augmented reality character animation. We can say that it interacts with the physical floor closely. It will jump into the floor, and we can say there are still some shadows here. So this kind of AR character animation will provide us with the immersive experience and the engagement. So it has been applied in a lot of AR games like the Pokemon Go. So if we want to create this kind of AR animations, the typical workflow will we first script the character animations in the professional softwares on the desktop, and then we translate it and transfer it into the physical space. So here, but in the physical space, we cannot edit. So here is a gap between the editing or the creation workspace and the target scene. So to address this issue, our key idea is that we do not need any professional tools. We only use the mobile phone, like how we control or how we play with a doll in our childhood. We now control our mobile phone or mobile device to move it and perform some motion gestures, and then the virtual characters will follow our motion and the movement. But as we know that the mobile device, it only have the 6 degree of freedom. The virtual characters animations will have the high degree of freedom. For example, if I perform this motion gesture of a mobile device, which one is it? So it's hard to say. To solve this issue, we conducted 2 illustration studies. We do not define the motions by ourselves. We let the users to define the motions that they want to create for the AR character and the corresponding motion gestures for each motion. So here are 2 examples. We allow the users to move the mobile phone in the physical space to perform this kind of motions for each motion gestures for each motion. And then we collect all the motions and do some analysis and select one of the representative motion gestures for each motion, because for different motions, for the same motions, users may define different gestures, but we select the most commonly used one. And then we design and develop the AR animator system. So here, the user can directly manipulate the mobile device in the physical space and then perform this kind of motion gestures. Then using our mobile AR interface, they can edit it. They can add more details. Here are some results. We can say that the characters have the close interaction between the physical space. So this kind of interaction is very difficult to produce using the traditional interface. And here is another result. So following this work, we can also allow the users to control multiple mobile devices. They can produce the multi-character animation in a shared space. They can manipulate by their own, and then they can say from their individual views to say how their characters will interact with each other and also interact with the physical world. So the AR animator focus on the AR character animations. Besides the character animations, we also want to allow for the creation of the more general AR applications. So here, like in this example, this kind of AR application include the interaction between the between the human hand and the virtual ball, the virtual objects, and the physical object, the physical environment. So this kind of general AR applications is also hard to produce. The typical workflow to create this kind of general AR applications is similar as the creating character animations. The creators need to switch between the professional desktop software and the target application scenario for multiple times. So it is a very tedious process. And if the user is a novice user, he or she cannot do the programming. So how can they script for the interaction between the different physical or the virtual objects? So here we find three challenges. The first is that it requires the coding skills and the task. The users need to write the script for the interaction behaviors. And then is that it is inaccessible real world content. It means that when the users do the creation in the desktop software, he or she cannot obtain the real world objects. Only when they deploy or apply their content into the target space, they can say what is the real object is, where is their real world environment. And then is that they need to traverse between the multiple things. So it is a very tedious process. To address these challenges, we want to our goal is that we want the users to program the general AR interactions among the real and virtual content easily without any coding skills or without any complex the requirements of it. We say that here, as we show in the first example, here we have the real object, real environment, like the walls and the ground. And we also have the virtual object, like the virtual ball. And here, the virtual tree. So in complex AR applications, it usually includes this kind of different objects and the environment. But how can we program these general AR interactions easily? So we first analyze what is the general AR interactions, what is the different dimension of it. We analyze different subject and the scenario, and what is their spatial information or the triggering logic of it, because we say that the interaction behavior may contains a lot of chains. It is not just the event triggered interaction. It can contain a lot of complex behaviors. So here we first categorize the general AR interactions, and then we design and develop the ProInter AR. It is a visual programming platform for using the AR HMD head-mounted device and a tablet. So in the tablet, the users can use the visual programming by dragging the different blocks from the blocks workspace, and then it can they only need to consider the logic between the different interactions, and then our system will turn this kind of interaction into the code, and they will test this kind of AR interactions from their AR HMD. So here we have the scene creation UI from the AR HMD. They can create or specify AR interaction, and then they specify they do the scripting using the visual programming UI, and then finally they test and control manipulate different content to perform different interactions in the physical space from the AR HMD. So here we also provide the user interface for users to create the real world objects in our register different object in our scene, because we say that from our first challenge there is a gap between the real and virtual scene. So we want the users to specify or register the different real world environment and objects in situ. It means that they create it in the testing scenario for the target application. So we allow them to create the real objects and create the virtual object, and we also allow it to create different parameter values for it, because it can be used to script the complex interaction behaviors of it. And then the users can create this kind of interactive games or the demonstrations or the animations using our system. Here the users can to press the virtual buttons, and then the virtual car will directly move into the coins, collect the coins, or also when it collide with the physical objects, the score will be reduced. The users can use their surrounding objects to create different AR instrument game. They press different object, it will have the different sound. And for the education scenario, the teachers can use their surrounding objects to and with the virtual objects to craft what can be learned, what is difficult to learn, or what they want to demonstrate for the students. Here they use the virtual objects and the physical cup to show the physical concept.
Impression. Sunrise is an 1872 painting by Claude Monet, first shown at what would become known. The Starry Night is an oil-on-canvas painting by the Dutch post-impressionist painter.
So here is that the users want to create their own customized AR guidance.
Sunrise is an 1872 painting
that is created with their favorite characters. So the users can use the different physical and virtual objects create the interactive behaviors among them easily. So here, these two pillars together will help lower the barriers to create the intelligent and creative interactions using the AI and AR. So besides these works, I'm also working on to explore the cross device or the spatial UI adaptation. We know that the 3D user interface is an important component for the AR interaction. So how can we make it more adaptive, and how can we using our surrounding environment to put the different user interface or user interface component to can be easily used by the users, especially for the cross-device interaction scenarios. And then I also working on the AI for game design. To be more specifically working on the game mechanism, the game art generation and the creation using the AI. And also I work on the creativity support for both the digital 2D and embodied space. And beside that, I also working on the proactive agent for the user interaction. So we know that current user interaction is like that the users will provide something, and then the agent will respond with it. So if we with the AR device or the AI device, if the device can say say our environment, it can get more information of it. So we can like to design some agent that help it to understand the user's intention better, and we can also use their previous behaviors and content. Do not need to rely on the explicit prompts to infer the user's intention, and then we can generate the user interface or the content or their next action ahead of need. So we provide more proactive interactions for the users. So here are all the publication, and thanks for my collaborators and for their contribution and effort. So this is the end of my presentation. So if you have any questions or suggestions, feel free to let me know. Yeah. Okay, thank you.
Yeah, thank you very much, Professor Ye, for your sharing of your latest work. We have some questions for you.
Yeah, okay, thank you.
So, the first one is about your work on game design and then the animation creation. So, how did you see the rule of AI shifting from the rule of builder the game to the director or to the planner of the game?
Yeah, I think it's a good question. Thank you, Professor Luo. We say that in the early stage that the AI will help us to directly generate something, generate the assets, generate the
Yeah.
game art image, right? But
Yes.
currently we know that I think this kind of asset or the art is just a part of the game, because we know what is the game can attract the player. The asset or the style or the content will be important, but another part is the gameplay, the mechanism. So I think maybe with the limited knowledge to this kind of gameplay or game mechanism, the AI will cannot do it well. But we know that the users will have we have better understanding of different knowledge of it. So here maybe the AI can play as a role as a co-creator with the human. Maybe the human can provide more like the specific information or knowledge of this kind of gameplay or mechanism and what they want, but AI can help us to explore what is missing in the current like the data set or their knowledge graph. So then they can collaboratively build something instead of just let AI to generate everything.
Okay,
Yeah.
thank you. And how do you think about the native AI game? And there is a trend of they say the native AI game, which is includes a lot of randomness.
I think the randomness it is like an interesting or surprising part in the game. So if we can build everything that is in our control, the players may find it is boring once they play it for one time they never played. So I think from this point from this perspective, this kind of randomness will help us to create more opportunities for the game.
See, and your work is about lowering the barrier of the content creation. But could you please share one of the failure or unexpected outcome of your uh, recent research?
uh I think it's a good point. And um, so for my recent approach, that is and surprising point is that so currently I'm working on this kind of creativity support. It means that uh, we want the AI to provide some opportunity or to help us to find some interesting or creative or novel ones. So at the beginning, I think that I want to rely on how AI can provide or generate something for us. That especially like for a game, I want some interesting game ideas. I want AI to generate for me. But when we work on it, we find we discuss with the potential users or our target users. We find that it is just to reflect your previous question. Is that we actually they don't like AI to generate for something for it, generate everything for it, because they sometimes want to benefit from the skills that AI can provide it. So from this perspective, we do not only want to generate something, we want to guide the user. We want to guide how they can benefit from the instruction of the AI, and then with these instructions or the guidance, they can think more ideas. We think it will becomes the skills of the user instead of they do not need to rely on AI. Although we usually want to do, usually do it, like we heavily rely on AI, but we want to turn this kind of dependence into the skills for the users, and the users really appreciate this aspect. So I think it is very surprising, and it is not in our scope at the beginning.
Yeah, thank you. Your work on game design is very interesting. Have you ever connect with the game studios, say in Tencent, to discuss the plan for developing games together?
Yeah, actually, we are working on some industries like the Tencent and other companies because they have a lot of resources for us, and
Yeah.
we have this kind of ideas for them. So I hope that we can collaborate together, like to hosting some game AI hackathon, or that we can attract more people by producing some like the open source softwares they can directly use for creating the game AI related applications.
Okay, thank you. We will look forward to the game.
Okay, thank you, thank
And
you.
yeah, that's all the questions. Thank you very much, Professor Ye, for the insightful sharing. Now we will switch to the second talk.
Okay, thank you.
Okay, thank you. Uh, yes, so we will now to the second talk by Professor Ho from Zhejiang University. And Professor Ho is a 100 tenants plan researcher at the State K Laboratory of CAD and CG in Zhejiang University. He specializes in graphics, computational optics, and artificial intelligence with a focus on light transmission. His research interests includes physically realistic neural rendering, optical neural networks, and 3D generation and reconstruction. He has published over 100 papers in top conferences and leading journals, including Nature Communications, TOG, SIGGRAPH, CVPR, and Neurops, with notable achievements, including 2 ASM TOG cover articles and recognition in the CVMJ annual highlights and the CGF top cited papers. In addition, he has served in various organizational roles for major academic conferences like SIGGRAPH Asia. His work has been successfully applied to platforms developed by companies such as ByteDance, Huawei, Vivo, Core, and Ray Cloud. His contributions have been recognized with honors such as the Qizhen Outstanding Young Scholar Award and the Youth Innovation Award from Zhejiang University. Now I will give time to Professor Ho for the talk.
Everyone, good night. Today, I'm about to introduce my work on the global neural rendering pipeline. The central question is how neural representation and AI native computation can improve and complete the rendering graphic stacks from scene assets to light transportation to the final display of images. I will cover the motivation first, and then our technical milestone and some system we are currently building. Photorealistic rendering aims to reproduce a continuous sequence of images that looks and behaves like the real world. So realism is not only a virtual similarity in a single frame, it also requires stable geometry, material, lightings, motion, and camera response over time. This comparison illustrates the target more clearly. Convincing imagery must preserve fine appearance cues while remaining temporal consistency. As we move from a simplified representation toward richer assets and lighting, the scene becomes more believable. But computational cost can also rise quickly. Realism emerged from 3 connected stages. First, asset representation determines what geometry and material details the scene can express. And second, the lighting computation models occlusion, reflection, transmission, and indirect illumination. Third, post-processing converts rendering signals into a display-ready images through exposure, color, camera effects, and reconstruction, tone mapping. So the neural technology and AI technology has now reshaping the all 3 stages. However, accurately representing the real world is expensive. For example, geometry might contain wear, aging, and microstructure surface. So the cost of a conventional mesh grows rapidly with the details, and materials are often represented by compact analytical models. But complex appearance may require measurable data such as BTF, which reduce the flexibility and increase storage. And the core tensions is therefore expressive power versus the budget for storage, queries, editing, and real-time execution. And regarding the neural geometry, it improves the neural representation effectively and also enables new asset form like 3D-GS. Also, we have other options like MBVH that encodes local surface with neural networks and combines them with a hierarchical structure for multi-scale query and ray interaction. An unified Gaussian primitives explore a common theme primitive across meshes, volume, and 3D Gaussian representation, and also the relighting problem of this neural primitive is also a recent concept. Nonetheless, the most challenging part is the neural material and its lighting. The neural material research focuses on the expression and compression of high-dimensional functions such as BRDF, BTF, and BSSRDF. Those materials are relatively easy to encapsulate as local computations, so they are also promising for productions. So recent work include neural texture compression and real-time evaluation of complex appearance. Hardware and API support, include cooperative vectors and neural shaders, is gradually making small networks a practical part of graphics pipeline. The most challenging part is actually the lighting and also, for example, the light transportation, which requires recursively solving the rendering equation, which generally has no analytical resolution for a real thing. Path tracing estimates the high-dimensional integral by randomly sampled light transport paths. With few samples, the estimator has high variance and variable noises. Increasing the sample could reduce the variance, but tracing and shading codes usually grow almost linearly. This trade-off motivated learning prediction and reconstruction of the light transportation. In summary, to enable this complicated simulation in real time, traditionally, the community resolved to a co-design architecture, including both hardware and software, called rendering pipeline. The first major hardware transition moved graphics from fixed local shading to a programmable GPU, and the second chain added dedicated ray tracing cores, making global illumination more practical while regarding the mesh-based pipeline. The next transition might bring neural computation directly into the rendering architecture rather than using AI only as an external post-processor. So we have noticed this tendency several years ago and start our project. The tendency for moving from traditional computation to AI is rapidly become standards on both PCs and mobile devices. The important point is that not only a single product announces it, but both hardware and software platform consider the AI as a standard computational platform. And also, there are other opportunities. For example, the capability. The neural processors can deliver larger throughput gain on interface-oriented workloads. This creates a room for learned functions that could have been too expensive, including inside a conventional real-time graphics loop. So it might provide that the memory access and execution patterns are carefully decided. The second opportunity is the efficiency. The computer performance per watt has become as important as peak throughput, especially for laptops, mobile device, and some embodied systems. And neural representations can trade expensive explicit computation and storage for compact inference. But the overall image cost must still be measured at the system level. It's more efficient than the traditional pipeline. And also, we have a larger community in terms of AI. The community graphics is now increasingly connected with computer vision, embodied intelligence, and large language LLM models, and generative AI. So the shared memory, the neural representation can potentially support such change by including the rendering and perception simulation in the AI native method. And also including the ecosystem, the AI and GPU now have different types of community, while the AI has dominated the development of the PC. So all these observations bring us to a new target. What should the rendering pipeline looks like in the AI era? We might use a pure video generation that offers impressive synthesis but the control and consistency remain difficult. So our goal is to build an intelligent graphics pipeline, which retain the explicit scene structure, the global illumination, and controllable assets while using a neural computational, where it provides the most value. The long-term goal is to build an AI native rendering pipeline that processes units and with a unit processing devices and completing rendering software architecture. And this slide basically they summarize the conventional pipeline with our AI native pipeline. In the traditional pipeline, we include stages such as vertex processing, rasterization, shading, and blending. This might remain useful, but with this, we introduce 3 learnable components: the general lighting-oriented model, the object-oriented model for specified transportation, and image-oriented isolation model. So with these 3 new model, we might be able to eventually integrate and build an AI native process that without the help of traditional GPU. So we start on this project on 2021. In the first phase, we focus on the theoretical foundation. We ask whether the neural lighting could be decoupled, scaled to complex illumination and scenes, and generalized to beyond one narrowly trained effects. And the next slides will summarize the 3 milestones that we resolve during this stage. Our theoretical, the first thing is that decomposition. Decomposition separates the light transport into reusable and generalizable functions. The scalability handles many objects and complex illumination without linear growth in runtime cost. And the generalization moves from a scene-specific predictor toward a common illumination model. Together, these 3 steps define the foundation of the global neural rendering pipeline, and which we will detail in the next slide. First is about the decomposition. The primary and most important challenge is the decomposition, because the neural radius field is effective for visualization, but the rendering system must respond to the change in objects, materials, and lightings. So our first work nailed decompose the scene into object-oriented neural lighting transport functions. This makes shadowing, reflection, and color bleeding and other effects controllable instead of baking everything into one static radiance field. This is a key line of work from our lab. The objective is to build a dynamic global illumination prediction. When an object, material, or lighting change, the rendered result should update without retraining the entire thing. Nailed provide the initial object level decomposition and establish the structure for the following extensions. We separate direct and indirect illumination and then model the associated transportation functions. Direct transfer capture the immediate response from the light to the surface of the object, and indirect transfer represent the more difficult multi-bounce contribution. Combining these two, we produce the final global illumination estimate by keeping the components interpretable and editable. The architecture starts from object-centric scene observation, light, foreground, and background observation, and the information. They are all encoded separately. And hyper networks can neural architecture generate object-oriented representation, while the G-buffer provide geometric guidance. And this structure led the network to transform and compose the object contribution rather than treating the complete imagery as a undifferentiable signal. Here we show the decomposition at evaluation time. Each object contribute directly and indirectly transfers, and these contributions are assembled into the final global illumination images. The important property is modularity. Objects can be moved and combined while their learned transport remain meaningful. Here are the example. Because the global illumination is a highly complicated physical phenomenon, learning the global light transportation function is kind of similar to learning some difficult part of the world model. So this visual comparison demonstrates why explicit decomposition matters to learn such physical effects. Previous works use generic neural things representation that might reproduce the training views, but it can struggle when the scene configuration changes. And our representation that with the decomposition is designed to preserve the relevant transport structure, producing results closer to the ground truth under dynamic things. Okay, and given this decomposition, we then make an extension on it that use super user implicit deformable feature field. Each object now has a multi-dimensional solution feature representation, and multiple object fields are composed into a common thing. This supports more dynamically configuration and richer effects such as soft shadow, caustics, and indirect highlights, while keeping the representation object-oriented representation. Here are some results. We show that our prediction across different configuration focus on the stability of shadow, reflections, and indirect colors, such as when the object is moving. The objective is not only to low image error, it's also the result is also response to the immediate and physical plausibly the immediate physical change and produce physically plausible results and in real time. Also, we demonstrate our models in more challenging things such as including some expressive range of dynamic global illumination, including the refractive and reflective effects, and all these challenges and lighting and material effects can be included in our in a unified model. Given the composition, now the composition effects, now we can turn to the second challenge, the scalability. We built our second work, the Lightformer, in 2024, which enables the encode the virtual point light and as a latent feature and gather their contributions through attention. So we use a G-buffer and shading clue to guide the decoder while compose the neural lighting representation, summarize many illustration samples. The purpose is to avoid evaluating separated expensive models for every individual object and lighting. Benefit from this decoupling model influence the object and lighting numbers. The system now responds to dynamic change without linear increase in the cost. The same lighting encoding and gathering structure can represent the changing illumination by keeping runtime iteration bounded. This makes the architecture more suitable for interactive application than a model tied to a fixed lighting configuration. Now, there are some examples. We show that in this light transportation oriented model, we can we can support a dynamic scene with hundreds or thousands of moving objects. They are fully animated, and also including a dynamic lighting. So now we can support an AI level, a game level application. Finally, in last year, we resolved the third challenge, is the generalization. Instead of training an independent network for everything, we construct a large-scale dataset and train a general rendering model. The new life is our important step toward learning reusable illumination behavior across diverse content rather than one environment. We built about over 100 things, 1 million things. And this video shows that the model can generalize to another tens of millions of unseen configuration and lighting, and they can all generate plausible visual details in these challenging cases. Altogether, we use these three fundamental material to build the decomposition, the scalability, and the generalization to decide a final rendering pipeline, a complete system that rather than an isolated research targeted. Now the resulting architecture combines a general model that with the optional specialized model and accelerating models. The general component handle broad illumination behaviors, and the specialized component address effects that needs dedicated capability. And the acceleration component reduce the cost in image space. These models altogether organize the form of our global neural rendering pipeline. And this picture that we showed before. Here, the concept is mapped back on concrete graphic stage. The neural function do not replace the whole rendering at once. They augment the representation, the lighting, the surface evaluation, and post-processing, while remaining the compatibility with the rasterization, ray tracing, Gaussian splatting, and other existing assets. Then we try to figure out the capability boundary of this pipeline and why the theoretical foundation is placed. We test with various graphic tasks. And this chart is our evaluation framework. The horizontal characterize the span, characterize lighting, material, indirect effects, hair, skin, participating media, liquids, shadow, caustics and reflection, and fabric, all kind of common rendering effects. We compare traditional ray traced and neural rendering pipeline to identify both the advantage and the remaining gaps. We start from the dominating effects, the lighting. For many light rendering, conventional real-time solution often rely on ray tracing plus denoising, which can introduce noise, screen space artifacts, and ghosting. The Lightformer is our neural rendering model that uses a pure rasterization-oriented neural path. It adds no Monte Carlo noise and avoids screen space reconstruction artifacts, showing how a learned model can change the quality-cost trade-off. Also, for complex illumination that express another trade-off, linear transform the cosine are fast, but mainly support polygonal lines and do not model full shadowing. In our neural complex illumination model, it supports arbitrary lighting and integrate the shadows, but might be offline and require training per line. And recently, we have resolved this problem and then move forward to arbitrary lightings with a real-time interval. inference, although the scene-specific training remain a limitation. But for example, in this video, we demonstrate our framework easily can handle easily handle the most challenging information with thousands of small light sources, which is impossible for traditional rendering, and also produce in our work. We also produce vivid reflection details at real time. So we here are some scores that we give these three kinds of methods. We found that the neural rendering pipeline can actually produce more promising results compared to all existing approach. And then we move to the shadow. Regarding the shadows, the neural rendering pipeline also produce more plausible results in a complex scene with difficult hard and soft shadows. And in contrast, the blurring or artifacts are inevitable in traditional or retraced pipelines. And in here, we also give three method score. And then we shift from the illumination to shadows and material. The material are an especially practical entry point because their evaluation is local, their inputs are structured, and their learned representation can be integrated into the pipeline. So they are very extremely friendly for neural rendering. And then we move to the indirect illumination. Indirect illumination is an important appearance effect, and because the same elevation principle applies, the compare controllability, fidelity, runtime, data requirements, and ease of integration, and this all this is very friendly for the the AI native rendering pipeline. As more effects are covered, the chart become a map of engineering choice, which effects can become in a general model, and which need specialized model, and which should remain conventional. Then we explore the effects such as hair, skin, and fabric. These domains often contain complex microgeometry, subsurface transport, making them promising target for learned representation, but also demanding a careful validation across material and lighting. Here are some results of our recent work that we compare, we produce a very plausible, basically reliable results in difficult and challenging error rendering that we combine 3D and our light transportation function to produce the movie level images in real time. Now, there are also other effects like skin, fabric, and all these are similar to the material. And we can find that such kind of effects are very friendly for the AI native rendering pipeline. Then we targeted at some challenging effects like the liquid and the high frequency or optical effects like gas. And these cases are visually sensitive. Small prediction errors can create a flicking and unstable highlights or incorrect energy distributions. But in the neural rendering pipeline, we can all outperform the traditional method. And this work is a recently published accepted paper by the AsiaGraphics Asia 2026. It accelerated industry quality liquid rendering from minutes to real time in 20 FPS with very plausible details. we both generate the physical simulation and the rendering at the same time in one model. Okay. And then we focus on some challenging problems like acoustic reflection and refractive effects. Acoustic is considered one of the most challenging rendering effects for decades, and which is basically no real-time solution until our model. And then we tax on the reflection effects that span multiple frequencies. While the rough surface produces a broad, low-frequency diffuse response, the smooth surface creates sharp, high-frequency specular details. So a robust model should both allocate representation capability according and maintain a continuous response as roughness change. This is a recent work in SIGGRAPH 2025, and there is a direct comparison with our method and the traditional ray tracing-based pipeline, and we can show that we have much stable temporal stability and more realistic photorealistic effect. Okay, and the final challenge is the refractive effects, which is usually there's also no solution until our model in rendering in real time. In here, we might obtain over 1,000-fold acceleration and achieve this kind of challenging effects in real time. In conclusion, here we summarize our complete validation. The general model can cover reusable illumination behavior, such as the lighting, the shadow, the material, and indirect illumination. And for other effects, we need specified specialized model for now, and maybe we can make a generalized model someday. But we need to consider the real-time performance and quality trade-off, considering the real-time rendering. Now, based on these two, the theoretical foundation and exploration of the boundary, we now move from research milestone to an ongoing system build-up. The current architecture integrates the general model, the specialized model, and the training infrastructure and runtime interface and hardware targeted in one systematic pipeline. So we build a joint lab, cooperating lab with some chip company, and provide to resolve this fundamental system work. The Zhejiang University contribute the rendering research, dataset, and other algorithms. And by the way, the community might help us build the chips, and we will go together to build an API. So first, regarding the engine, we have made a Z engine, which is AI native real-time 3D engine prototype. Here are two views, the model viewer, and we provide exactly access and scene workflow similar to the Unreal Engine. And while in the low level, we replace the traditional rendering pipeline with the AI native pipeline. And then regarding the model, we have already built a generalizable model that train on millions of things, and then we might move to other challenging cases such as embodied AI games and outdoor things. Regarding the trainer, our target is to build an automated training system. So specialized models can be trained with given a customized shader or some customized data. And this training system might return the final model parameters to the user so they can integrate the specialized effects into the pipeline anytime. Also, we are developing a lightweight PyTorch-based graphic interface that will replace the traditional OpenGL. Because the OpenGL is hard to learn, hard to use. Now we want to build an AI native language and API that support rapid prototyping, differentiable workflow, and automated training while keeping the path toward a high quality runtime integration. And finally, with this software stack, we ultimately want to develop on specified hardware system. We therefore we are currently we are pursuing two tasks. One is the adapting the existing AI native hardware, and the second one is design a dedicated hardware that have higher performance. For the to integrate the existing hardware in this pipeline, we can use, for example, programmable rasterization to use the existing triangle-based meshes and assets. And with this kind of system, we now can build a rendering pipeline in AI accelerator, AI native hardware like H100 and A100. Also, the second, for the long-term vision, we want to build an AI native graphic pipeline, graphic hardware chips that has dedicated for the high performance inference of the AI native pipeline. Okay, this is the, okay, thank you. This include my presentation. And if you have any question.
Yeah, thank you very much, Professor Ho, for the impressive results shown in the sharing. We do have some questions for you. The first one is, you emphasize the AI native pipeline rather than the AI accelerated pipeline. So in practice, what is the fundamental architecture difference between these two? Does the AI native pipeline abandon the traditional components like the rasterization, ray tracing?
Okay, the fundamental difference might be the dedicated chips. In an AI native pipeline, we don't require dedicated hardware designs such as programmable shader and article for accelerating the traditional rendering system. And so we now can save the space for this dedicated hardware to build a larger AI native compute unit. That's the fundamental difference. In addition to that, we might have more now the rendering pipeline, we have space to build a larger AI power. And also we don't need to we don't need to transfer the data from this dedicated chips to the AI unit. So this is another advantage. That's it.
Okay. And in a fully AI native neural rendering pipeline, what is the computational bottleneck?
For now, I think the scalability still has some challenges because as the number of lighting and dynamic objects increase, it's very difficult to maintain the high quality in runtime. But on the other side, we have already achieved much promising results compared to the traditional pipeline. Additionally, I think the memory bandwidth is also another bottleneck in terms of hardware, but this can be optimized, I believe.
Okay.
That's it.
Okay, third one. If we achieve a perfect AI native neural rendering pipeline, so what would happen to the traditional physically based rendering? Are they still useful?
I believe they will still be useful. That depends because the traditional physically based rendering, they produce the most reliable and plausible results. And when we are treating the high quality task like the design, like scientific computation, we still require such kind of accuracy. For the new AI native rendering, I believe it's more suitable for human interaction, uh, such as games and interactive movies and some interactive interface. Yeah, so I believe they are targeting a different domain. Yeah, that's it.
Okay. And another question is, what is your take on a render former? And more importantly, do you think a render former like pipeline can truly scalable?
Okay. Actually, we have showed that the random former pipeline is scalable, but it's not in the original the published works. We have developed the system and have many new evaluations and new progress. Now we are doing the test and trying to generate a robust system cooperating with some company. So I think the capability has been shown in the work, shown in the published work. The only now the challenge is the living challenge is how to scale up the system, scale up the data set. Yeah. So and also maintaining the runtime performance. And I believe these are all it's not a fundamental challenge, but they are engineering challenge.
Okay.
Yeah.
Okay. I think we have finished all the questions, and I would like to thank you again, Professor Hall, for the
Thank you.
insightful sharing. And here we have finished our two talks today, and we want to thank our two speakers, Professor Ye and Professor Hall again. And I also want to thank all the audience online in Bilibili and YouTube. Thank you very much for attending today's session, and we will see you later in the next time. Bye bye.